Hello and welcome to the second of our online lessons looking at sound. So last lesson we looked at the types of waves found in the physical world. We mentioned that transverse waves were these types of waves that go at 90-degree angles to the direction of the wave. What we mean by that is that they move up or down. And we said that longitudinal waves are waves that do not move up or down. Their oscillations are in the same plane as the direction of the wave. Now this topic is sort of split into two parts. We're going to look at sound first, and then once we've done all the lessons on sound, we're then going to look at light. So by the end of today's lesson, you should be able to describe how sound is produced and how it travels. You should be able to explain why the speed of sound is different in different materials, and you should be able to compare the speed of sound and the speed of light. So first thing we need to write down, and the first thing we need to say is because it's an important point, is that vibrating objects create sound. So vibrating objects create sound. Now there is a really simple experiment you can do to prove this. If you take your hand and you put it on your neck and you talk, you should be able to feel your voice box vibrating. That is a part of your throat known as your larynx, and your larynx makes vibrations so that you can make sounds that come out of your mouth. Okay? So vibrating objects make sound. They create sound waves. The second important thing we need to write down at the start of this lesson is that sound waves are longitudinal waves. Now last lesson we looked at what longitudinal waves were, and we used this diagram here. I'm going to use this diagram and then I'm going to use the one below to explain. So this diagram shows a longitudinal wave, and last lesson we said that you have these areas of compressions where the particles move closer together, and we have these areas of rarefactions where particles move further apart. We also said that the waves do not go up or down, they simply move side to side, and you should have watched a video with a slinky spring demonstrating this. So if we can make this a little bit smaller so that we can use it. So we can say next to this, so I'm going to change my colour pen because it's not really important, but we still need to write it down, that longitudinal waves have areas of compression and rarefaction. Okay, so we have these areas of compressions where the particles are squashed close together, and we have these areas of rarefaction where the particles move further apart. Now to show how this looks in reality, I've got a second diagram which we can add underneath here. So if you look at this diagram, you can see we've got the sound being made from what's called a source. The particles are compressed right next to the source, where they then rarefract. They are then compressed, rarefract, compressed, rarefract, compressed, rarefract. This is a longitudinal wave. Okay? So I can just make this a bit smaller. Oh, look at that. It's exactly the same size. Sometimes I sort of amaze myself with how brilliant and perfect I am. So we can label this up. So this is what's known as the source. So this speaker here is the source. Now a source in terms of sound is something that vibrates to create sound. So a source is something that vibrates to create sound. something that vibrates to create sound. Okay, so this is something that vibrates to create sound, and in this diagram we've got a speaker that is vibrating, causing vibrations to create sound. We get this compression and refraction of particles in a medium which creates sound waves. So I'm going to write down, in fact I'm going to use a different colour, compressions and refractions of particles in a medium create longitudinal waves we call sound. So we have these refractions and we have these compressions of particles in the medium, in this case air, which cause these longitudinal waves. So on this diagram we've got our source here and we've got our particles in the medium found here. So these are our particles in the medium. Particles in medium. Now, this word medium seems to be cropping up quite a bit. If you have a look, we've got the word medium here, and we've got the word medium here. Now, in lesson, this would be where I say, who wants to have a guess what the word medium means? But because obviously I'm sat in my office at home, all alone, recording this video, I can't do that, can I? So, we're simply going to define it. So a medium is simply a solid, liquid, or gas. Okay, it's an area where particles are found. So we can say an area where particles are found, and we can add underneath there, and I'm going to put it in red, always a solid, liquid, or gas. Okay? So it's an area where particles are found, and it's always a solid, a liquid, or a gas. Now, it's probably worth defining here that there are areas known as vacuums. Vacuums. Now, in a vacuum, there are no particles. So, a vacuum, V-A-C-U-U-M. U-U-M. Now, we can define a vacuum as an area where there are no particles. So a good vacuum example would be space. In space, there's no particles, therefore it's defined as a vacuum. We are currently in a gas that we call air, the atmosphere. Therefore, we walk through a medium. You don't tend to feel that medium because your body is used to it, but we are constantly surrounded by particles. A vacuum is an area where there's no particles. Now, we can just add a couple more things before we move on. An example of a vacuum, so e.g., would be space. Space is an example of a vacuum. And we can also add underneath here, but in red because it's important, that sound cannot travel in vacuums as there are no particles to vibrate. As there are no particles to vibrate. Okay, so we've said that vibrating objects create sound. Sound waves are longitudinal waves. We said that a longitudinal wave has areas of compressions and refractions, and we use this diagram from last lesson. We got this area of refraction here and this area of compression here. We said that a source is something that vibrates to create sound. So our source would be such as a speaker. It's vibrating, which is causing a compression of air molecules. They then refract, compress, refract, and this makes what we call sound. So we get these areas of compression, refraction, compression, refraction, compression, refraction. This air is an example of a medium. A medium is an area where particles are found. This can always be a solid, a liquid, or a gas. Areas that do not have particles are known as vacuums, and an example of a vacuum would be space. Sound cannot travel in a vacuum because there are no particles to vibrate. So if we have a look back at our learning objectives, it says, can you describe how sound is produced and travels? You should be able to tell me it's produced by vibrating objects and that it travels by causing the compression and refraction of particles in a medium. Our second learning objective says, can you explain why the speed of sound is different in materials? So if we refresh this, obviously if you didn't get all that written down, you can always just pause the video and rewind. You're not limited to waiting for me to talk. If I bring up my white pen again, and we can pose the question, how does sound travel in different mediums? So how does sound travel in different mediums? And we can underline that, we can make that a sort of subheading. So to do this, we need to think about what particles look like in different mediums. So the three different mediums that we've mentioned, so what I'm going to do and what I would like you to do in your books is I would like you to draw three rather large boxes because we're going to draw what substances look like in different mediums. So three rather large boxes like so. It's very difficult to do this on a drawing board. There we go. I'm used to the whiteboard, as you're all aware. And just for your reference, I'm going to be drawing particles in this pinky colour. So I'm just going to put a key up here, particles. Okay. Now the first one that we need to draw is a solid. A solid. Now you should have learnt in science, so solids, you should have learnt by now that solids have their particles arranged very closely together and the particles are arranged into set layers. There's no randomness of the particles. They're arranged into these layers. Every particle is touching another one and there is very little space between the particles. Can I point out, when you're drawing these diagrams, make sure you make the particles nice and big. Don't do little tiny particles, otherwise you're going to be there forever, okay? So, in a solid, sound travels at its fastest, okay? So we can say that sound travels fastest in a solid. Okay, so sound travels fastest in a solid. Approximately in a metal such as steel, sound travels at 5,000 meters per second. So we can say that in solids, sound travels at 5,000 meters per second. Now, the reason they travel this quickly in a solid is because the particles are all touching. If this particle here starts to vibrate, it's going to bang into all the particles around it, causing them to vibrate, and then these are going to bang into the particles around them, causing others to vibrate. Okay, so you need to make sure that when we're looking at mediums such as solids, liquids and gases, you always keep in mind that the particles are close touching in a solid, therefore if they start vibrating, they pass this on, causing sound to travel quickly. So we can say, underneath, we can just write down, and I can use a different colour, let's try this blue because I haven't used it before, that if, oh that's nice, if one particle vibrates in a solid, comma, all surrounding particles will be forced to vibrate. Will be forced to vibrate. So in a solid, sound travels at its fastest. It travels at 5,000 meters per second. That's because they are arranged into these layers. They're all touching. Therefore, if one particle starts to vibrate, the others start to vibrate. And this makes the sound travel quickly. There's no gaps between the particles. So we can just add underneath here, there are no gaps between the particles. Right then, the second one we need to look at are liquids. Liquids. Now you should have learnt that in a liquid, the particles, although they are touching slightly, they're not arranged into any sort of arrangement. Okay, there are small gaps between the particles, unlike in a solid where we've got these clear layers. In a liquid, we don't have that. Okay, so in a liquid, sound travels at about 1,500 meters per second. So in liquids, sound travels at 1,500 meters per second. Okay? Now the reason it travels slower is because there's gaps between the particles. Although they are touching, they're not arranged into these layers. Therefore, if this particle starts to vibrate here, it can only make this one vibrate, which can only make this one vibrate, which can only make this one vibrate. These gaps don't allow the sound to transmit directly from particle to particle. So we can say, and I'll put it in red, small gaps between particles in a liquid slow down, in fact I should say liquid, not liquids, in a liquid slow down how quickly sound travels. Okay? The final one we need to look at and talk about are gases. Gases. Okay? Now, if we were to draw the particles in a gas, we would just need to draw particles spread out with large gaps between them, like this. Okay? Now, for this reason, the particles do not transmit sound very quickly. They do transmit sound. That's why you can hear me talking at the moment, because my voice box is making particles in the air vibrate, which is being detected by my microphone. That's then causing vibration in your computer or iPad or whatever, which is then sending the sound to your ears. But it is very, very slow. So we can say sound travels slowest in a gas. It travels at 340 meters per second. So sound travels at 340 meters per second. 340 meters per second in a gas. Now, this is because there are these large gaps between the particles. So if one starts to vibrate, it's very difficult to make the next one vibrate or the next one. Okay? So we can say, switch back to red, large gaps between particles make it difficult for vibrations to be passed between particles. So large gaps between particles make it difficult for vibrations to be passed between particles. Now, if you just look at this page, there's a lot of red pen. That means there's a lot of important points here, okay? So we've said that solids, sound travels fastest in a solid. In a solid, it travels at about 5,000 meters per second. If one particle vibrates in the solid, all surrounding particles will be forced to vibrate. So if this one vibrates, this one will, and this one will, and this one will. They will each pass the vibrations along. In a liquid, sound travels at 1,500 meters per second. This is because there's small gaps between the particles, however they are still touching, so the vibrations can be passed along, albeit very slowly. In a gas, sound travels its slowest. It travels at 340 meters per second. This is because there's large gaps between the particles, so if this particle starts to vibrate, it won't really pass on the vibrations to this one or this one. It does eventually pass it on due to these rarefractions and these compressions, but it is much slower than in the other two mediums. Remember that these are all mediums, solids, liquids, and gases. So, if we have a look back at our learning objectives, it says, can you describe how sound is produced and travels? It's produced through vibrating objects and it travels as a longitudinal wave. Can you explain why the speed of sound is different in different materials? This is because the particles are more close in different materials, therefore they pass on vibrations. The final one is, can you compare the speed of sound and the speed of light? This should be a fairly easy one to do. I wonder if I can just turn everything back to black like this. No, it's going to take forever. So I'm going to just wipe the board and turn us black. Okay. So, we've already said that sound travels at 340 meters per second in air. So, we can say, in fact, I'll just use this pen. In air, sound travels at 340 meters per second. Now, in air, light travels at 300 million meters per second. So it's almost 1,000,000 times faster than sound. So we can say that light travels, if I can spell travels, at 300 million meters per second. It is 1,000,000 times faster. So we can, or almost 1,000,000. So we can say light travels at almost 1,000,000 times faster than sound. So all you need to know is that light is much faster than sound. That's why, if you think about it, when we have a thunderstorm, so I'm going to draw you a nice little rain cloud here. When we have a thunderstorm, you first of all see the bolt of lightning come down from the sky, and then a couple of seconds later you hear the... So what you get is the flash. It's not at the same time. You always see the light before you hear the sound. Right then, so that's all of our learning objectives covered. What you need to do now is you need to answer some questions so that we can then mark them. So if we just pull up the questions that we want, what I would like you to do, please, is I would like you to pause this video now. I would like you to have a go at the questions that are currently on the screen or on the PowerPoint if you've got it open. For the first question, you need to copy out the sentences, filling in the gaps. For the second question and the third question, you need to write out the question before answering it in your books. Make sure you've got a green pen or a different coloured pen so that we can mark these in a moment. So pause the video now and start having a go at these questions, please. Alright then, so you should have had a go at these questions. We now need to work through them. So if I can just paste this first question in, make it a bit bigger so that we can annotate it. In fact, that's maybe a bit too big. We don't need it that big, do we? So let's have a look. So this would be where I normally pick on you, as you're aware. Could you please just correct your answers with a different coloured pen as we go through it? So sound is produced by objects that are vibrating. So sound is produced by objects that are vibrating. This makes the air molecules vibrate, and produce a sound wave. Sound travels fastest in a solid or in solids, and slowest in gases. It cannot travel through a vacuum. So it should have read, sound is produced by objects that are vibrating. This makes the air molecules vibrate and produces a sound wave. You could have also had oscillate there. sound travels fastest in solids and slowest in gases, and it cannot travel through a vacuum. So our next two questions, if I can just paste them in, our next two questions look like this. If we can just make it a bit bigger, there we go. So the second question says, explain why sound travels slower in a gas compared to a liquid. So you should have said that gases have larger gaps between particles, and therefore vibrations cannot be passed on easily. Cannot be passed on easily. Doesn't mean they can't be passed on, but it's not as easy as in a liquid. So for your 2 marks for question 2, you should have said that gases have a larger gaps between the particles, therefore the vibrations cannot be passed on as easily. The third and final question, it says, compare the time it takes the light to travel from your teacher to your eye with the time it takes sound to travel the same distance. So obviously, I'm not going to write it all down, but we can draw some simple diagrams. So if we've got you guys sat at your desk at school, so that's you sat at your desk, there's your chair, and you're all listening to me teaching. Obviously, I'm really, really cool, so I'm going to draw myself some biceps, like so, because of, I'm hench. And I'm teaching you guys, okay? If we're talking about sound waves, so in orange I'm going to put sound, the sound is travelling through the air, which is a gas, so the sound is travelling through the air, so the medium is gas, and it's travelling at 340 meters per second. If we're talking about light, so light travels at 300 million meters per second. So the light that is bouncing off me is travelling at 300 million meters per second. So you should have said, when it says compare the time it takes for each one to travel, you should have said light rays reflect off the teacher into your eyes at 300 million meters per second. So light rays reflect off the teacher for 1 mark and travel to your eyes at 300 million meters per second for your 2nd mark. For your 3rd mark, you needed to say that the teacher produces vibrations in their voice box for a 3rd mark. For your 4th mark, these vibrations travel through the air as a longitudinal wave. So for your 4th mark, these travel through the air as a longitudinal wave. For your 5th mark, you needed to say that they travel at 340 meters per second. You could have then, for your final mark, said that light travels almost 1 million times faster than sound, therefore you see your teacher before you hear the sound. So that concludes our lesson on sound and energy transfer. If you are absolutely stuck with anything and you don't understand one of the questions or you don't understand something, please do not hesitate to comment in the Google Classrooms or even send me an email. I'll reply to you as soon as I can. Thank you very much, and I will see you next time.